If you've ever looked up at the night sky and watched a comet streak by, you will know of the wonder of watching one of these celestial visitors. Often seen with awe or fear throughout humanity's history, these bright-tailed objects in our skies were known as harbingers of change. And yet, in the last 50 years, the tables turned on these icy wanderers, and it went from them coming to visit us to us being able to visit them. Scientists had long wondered about the nature and origin of comets. Where had they come from? How were they formed? Are they the origin of water and life here on planet Earth? Over the course of the last 40 years, space agencies around the world have launched a series of incredible probes and satellites that have brought comets out of the realm of superstition and into the scrutiny of scientific understanding. Our understanding has evolved, and many models and assumptions have been broken. We did not understand comets like we thought we did. It's time to find out what we learned. I'm Alex McColgan, and you're watching Astrum. Join me today with this supercut as we explore the evolving story of comet science, from the missions that first imaged them, to the ones that caught their stardust, to the first moment a probe set foot on a comet's surface, and all the discoveries that followed. Let's start at the beginning. Humanity has been watching comets for a long time. Comets are regular visitors to the inner solar system. Some are spectacular, known as great comets, which are visible to the naked eye, sometimes stretching across a huge portion of our sky. However, most comets come and go without much of a fuss, not visible to the naked eye, and we wouldn't even know about them were it not for telescopes constantly monitoring sections of our sky. It is thought that there are billions of comets in our solar system. Comets come in three categories: short, intermediate, and long periods. Short period comets orbit as far out as Jupiter. Intermediate comets can be found around the orbit of Neptune and into the Kuiper belt, and many more beyond that are found in the Oort cloud, which are known as long period comets. Comets tend to have very elliptical orbits, with most taking tens of thousands of years to make one orbit around the Sun. Due to their tiny size and huge distance from us, most only get discovered when they approach the Sun in their orbits. Volatile material on their surface, like water and carbon dioxide ices, heat up upon approach, sublimating into space with some force, producing the bright coma and tails comets are famous for. This makes their detection a lot easier for astronomers, but once they whip around the Sun and head back out towards the outer solar system, we often never see them again, not in our lifetimes anyway. Most of the great comets we see are long period comets, meaning we'll only see them once in their millennia-long orbits. All except one, the poster child of comets, and the one you're most likely to have heard of, Halley's Comet. So let's start with this one, as Halley's Comet had an instrumental role to play in science's evolving understanding of these beautiful objects. While Halley's Comet is an intermediate period comet, every orbit has always produced a fantastic spectacle to those observing it, making it the only intermediate period great comet. Its orbit takes roughly 75 years, meaning someone could see it twice in their lifetime. And incredibly, there have been records of Halley's Comet dating all the way back to 467 BC. With the regularity and predictability of it lighting up our night skies, it was no surprise that it became one of the first comets we ever tried to visit. It was not the first. That honor went to comet Giacobini-Zinner, which NASA's International Cometary Explorer, or ICE, visited in 1985. But ICE didn't have a camera, which meant that no images were taken of that first encounter, just some scientific readings that detected water and carbon dioxide, helping scientists further develop the theory that comets were just dirty snowballs floating through space. But more missions were coming, a lot more. As Comet Halley returned to our region of the solar system, many space agencies scrambled at the chance to get a close-up look at the great comet's nucleus for the first time. And the result? Something known as Halley's Armada. The Halley Armada is the unofficial name of 5 separate missions from 3 different space agencies that all approached Halley at roughly the same time. One probe, called Giotto, was an ESA mission. Vega 1 and 2 came from a joint venture between the Soviet Union and France, and the final 2, Suisei and Sakigake, came from ISIS, later to be known as JAXA, or the Japanese Space Agency. Each of them has a pretty interesting story. We'll start with Vega 1 and 2. These Vega missions were primarily designed to drop off probes at Venus, but it was determined that the mothership portion of the mission could be redirected using Venus's gravity to do a flyby of Halley if it was timed just right. This gravity assist would prove useful, not just because of the speed boost the probes gain from the Venus flyby, but the redirection was particularly important as Halley has a rather unconventional orbit, which makes a rendezvous very tricky. Its orbit is highly elliptical, is retrograde compared to the planets in our solar system, and is inclined by 18 degrees to the ecliptic, meaning most of the time it is under or south of the solar system's plane. These 2 probes are twins, identical spacecraft that launched within days of each other from Kazakhstan. They arrived on the 6th and the 9th of March 1986 respectively. These 2 probes, while perhaps not the highlight of the Armada, collected a host of data, including photos of the nucleus, observations of its temperature, its surface properties, and composition of the coma. They both flew by Halley at a distance of only 8,000 kilometers. But interestingly, their positioning data was then passed on to the Giotto team, due to be arriving a few days later, which allowed them to increase the accuracy of their flyby, meaning Giotto could fly past Halley at an altitude of only 600 kilometers. But before Giotto arrived, the Japanese Space Agency's probes were approaching. This was Japan's first deep space mission, and as such, the Suisei and Sakigake probes were quite basic, and the missions were more about a demonstration of the launch vehicle rather than the probes themselves. Sakigake was launched first and didn't even have a camera on board, but instead had instruments to measure magnetic fields and plasma in interplanetary space. Upon the success of the Sakigake probe, Suisei was launched a few months later, but this time with an imaging system and a solar wind detecting instrument. Japanese scientists were interested in the comet's huge coma, which was imaged continuously as Suisei passed through it on the 8th of March at a distance of 150,000 kilometers from the comet nucleus. Even at this far distance, Suisei hit 2 dust particles during its flyby. Sakigake observed from a much greater distance of 7 million kilometers at its closest approach on the 11th of March. Then it was ESA's turn. On the 13th of March, Giotto made the most ambitious flyby yet. Equipped with a color camera, scientists were keen to get their first close-up view of a comet's nucleus. Flying only 600 kilometers over a very active comet, scientists were worried that the spacecraft wouldn't survive. As such, all of the most important scientific instruments were tucked into the body of the probe as much as possible, with a shield at the front to protect it from collisions. As Giotto approached, it took many pictures, and in this motion interpolated video of those images, this is what it saw. For the 1980s, this view is pretty incredible. Just after this approach, however, and just as scientists feared, Giotto was hit by some particles which sent it spinning out of control, meaning its antenna was no longer pointed at Earth. For an agonizing 35 minutes, the mission controller's screen showed no contact with the probe. But then, as perhaps hope seemed lost, contact. Giotto had stabilized itself again and re-established contact with Earth, sending back the valuable data it had collected. Giotto largely survived the encounter, although a particle had struck and disabled the camera on board, but thankfully not before it had taken images of its closest encounter. So what did all these missions discover about Halley? Well, the main thing that surprised scientists greatly was that Halley was a lot darker than they anticipated, as dark as coal. It was so dark, in fact, that it was beyond the limitations of the camera to distinguish details. The image you are seeing here is the result of serious image processing that bring out details from the original images. Also, only a small portion of the comet seems to be outgassing, seen mainly around these beams here. This contradicted the dirty snowball theory regarding comets. Instead, this data indicated comets were more like snowy dirt balls. The Armada also discovered that the comet's coma and tail included mainly water ice, but also carbon dioxide, methane, ammonia, plus iron, hydrocarbons and sodium. The dusty particles are likely caught up in the jets as the comet outgasses, blasting them away from the comet and into the tail. It's the dust particles ejected from comets that we see as shooting stars. That is how scientists are able to predict when meteor showers are likely to happen, as we can predict when Earth will pass through the remnants of a comet's tail. The brightness of the coma is due to the sunlight being absorbed and re-radiated by the ejected ices, and, to a lesser extent, due to the reflection of the sunlight off the dust particles. So, the brightness of a comet depends on how much it outgasses as it approaches the sun. Scientists also found Halley to be very fluffy, with a density of only roughly 0.6 grams per centimeter cubed, so it's likely to be porous or even like a rubble pile. Measurements showed that Halley's surface temperature was between 27 and 127 degrees Celsius, meaning only 10% of the surface was active as these missions passed by. But perhaps the most astounding discovery of all was the deuterium ratio found in its water ices, or the key indicator to show whether water shares the same origin or not. Scientists up until recently believed that comets are the source of water found on Earth. But this comet have shown that this likely isn't the case. The deuterium ratio is different between water found on Earth and water found on comets. The Halley Armada was an ambitious, multinational project to examine a frequent visitor to the inner solar system, which will be coming by again in 2061 if you want to put it in your calendars. The Armada uncovered a wealth of information about the outer solar system and the role of comets in the Earth's formation, but our understanding of cometary science was just starting to heat up. As the 1990s rolled round, we began to realize that comets could have a big impact on the planets of our solar system. And impact is the right word. In July of 1994, scientists around the world watched in amazement as the comet Shoemaker-Levy 9 smashed into Jupiter. The impact's blast was so powerful that it unleashed a force equivalent to 300 million atom bombs. For 6 days, Jupiter was throttled by 21 separate impacts from the comet's fragments, which produced giant plumes of debris that rose 3,000 kilometers above the cloud tops, an impressive feat considering Jupiter's immense gravity, and heated Jupiter's atmosphere to temperatures reaching 30,000 degrees Celsius. At the moment of impact, the comet was traveling at a blistering speed of 216,000 kilometers per hour, with its largest fragment spanning 2 kilometers in diameter. The impact raised huge clouds of debris that were visible for months and left a scar in Jupiter's atmosphere more prominent than its great red spot. Now, collisions of this magnitude aren't entirely unheard of. Our solar system is littered with evidence of major impacts from comets and asteroids. Scientists believe Earth was hit by a massive asteroid at the end of the Cretaceous period, which likely led to the extinction of the non-avian dinosaurs. But these events are extremely rare, meaning the chance to see one in action is a once-in-a-lifetime opportunity. So, what did it look like? And does the incident shed light on the odds of a similar event happening here on Earth? Let's take a closer look at the largest explosion we've ever witnessed. In 1993, astronomers Carolyn and Eugene Shoemaker and David Levy were conducting research at California's Palomar Observatory when they discovered a periodic comet that had been captured by Jupiter's gravitational pull. This was unusual, as most comets in the solar system orbit the Sun. However, Jupiter is so massive, being the largest of the 8 planets by far, that its ability to capture other objects approaching its orbit isn't surprising. A lot of Jupiter's irregular moons are likely captured asteroids and comets that have since burned off their volatile material on their surfaces. But this comet also had other unusual characteristics. For one, it was big. So big that scientists think that the frequency of similar impacts is a 1 in 6,000 year occurrence. But the comet was also fragmented, most likely torn apart by Jupiter's tidal forces on a previous approach. Most striking of all, however, was its highly eccentric orbit. Eccentricity measures the deviation of an orbit from a circle, with 0 being the value of a perfect circle and 1 being the upper limit of when an elliptical orbit becomes hyperbolic. Shoemaker-Levy 9's orbit had an eccentricity of over 0.998, in other words, extremely eccentric. Almost immediately, astronomers realized there was a possibility the comet would collide with Jupiter, but their suspicion turned into certainty once they collected more precise data. Before long, astronomers knew the impact would occur sometime in July 1994, and pretty soon the whole world was waiting for the event with bated breath. Anticipating SL9's impact, astronomers monitored its movements from the Keck Observatory, Germany's Rosetta X-ray telescope, and NASA's Hubble Space Telescope, among other instruments. But when the first of the comet's fragments hit on July 16, 1994, the worst-case scenario occurred. It looked like we would miss the spectacle. You see, SL9's trajectory meant the impact would occur on the side of Jupiter facing away from us. That meant none of Earth's high-powered telescopes were in position to view the initial impact. For scientists, this would have been a crushing disappointment. But as luck would have it, not all our cameras were located here on Earth. By sheer chance, NASA's Galileo spacecraft, launched in 1989, was only 1 year out from Jupiter at the time of SL9's final approach. It just so happened to be in a perfect position to record the impact as it happened. But Galileo wasn't our only helper from afar. The Ulysses spacecraft, which had been launched in 1990 to monitor the Sun, was also pointed at Jupiter. And even NASA's Voyager 2, located 44 astronomical units away, was programmed to monitor radio emissions from the crash site with its ultraviolet spectrometer. Each probe paused its own missions to work together on this to help us witness an extraordinary event. Shortly after Fragment A impacted Jupiter, Galileo saw a massive fireball erupt, reaching as high as 24,000 degrees Celsius. Its plume quickly rose 3,000 kilometers, which would make it as big as Australia from north to south. This was surprising, as scientists hadn't expected to see fireballs in the aftermath of the collision. A few minutes later, masses of ejected debris plummeted back towards Jupiter's surface and burned up, again turning Jupiter's atmosphere into a raging furnace. Before long, Jupiter's rotation brought the impact site into view of Earth, allowing high-powered telescopes like Hubble to view a huge dark spot on Jupiter. As it happens, Jupiter's rotation is fast, with days that last only 10 hours. Contrary to what you might think, larger planets tend to have shorter days than smaller ones. The comet's impact set off shock waves, which rippled across Jupiter's dense atmosphere at the speed of 450 meters per second. And all this was just from the first impact. For 6 days, between July 16th and July 22nd, the comet's fragments bombarded Jupiter, the largest coming on July 18th when fragment G hit. Its impact alone produced a blast 600 times more powerful than the world's entire nuclear arsenal, leaving a huge dark spot 1 Earth diameter across. However, as spectacular as the initial impact was, the comet's aftermath proved just as valuable. By studying the clouds of debris, scientists gained an unprecedented window into Jupiter's atmosphere and its movements. In addition, they caught a never-before-seen glimpse of Jupiter's composition beneath its dense cloud tops, as spectroscopic readings were able to identify material that had been splashed upward by the comet's impact. They detected diatomic sulfur and carbon disulfide, and heavy elements like silicon, iron, and magnesium. Interestingly, they also detected substantial amounts of water, something they weren't necessarily expecting. In fact, one of NASA's Juno probe's primary objectives is to locate where this water is hiding in Jupiter's atmosphere. However, one of the more disturbing implications of the impact was the realization that large celestial bodies could still hit planets. One school of thought theorized that major comet and asteroid collisions had been a lot more frequent earlier in the solar system's existence, but Shoemaker-Levy 9 made it clear that very destructive collisions were still possible. Had it happened by chance and we witnessed an extremely rare event, or does it happen more than we thought? Remember, we've only had the technology to see this kind of event within the last 80 or so years. If a comet as large as SL9 were to crash here on Earth, it would lead to the extinction of most life on the planet. This had a dramatic effect on our collective psyche, as anyone who lived through the 90s can attest. It was also a wake-up call for NASA and for various defense agencies. Before SL9, the term planetary defense didn't exist, but in its wake, NASA took up the mission of monitoring near-Earth objects, or NEOs, with the goal of identifying upwards of 90% of asteroids in our celestial neighborhood greater than 1 kilometer in diameter. Having achieved this goal, NASA is now well on its way toward identifying asteroids greater than 140 meters. But before you stay up all night worrying, be aware that these events are undoubtedly rare. And there is perhaps one other silver lining to SL9's impact. You see, Jupiter is a massive planet with a powerful gravitational influence. And since it is also one of the outer planets, some scientists now think it might act as a cosmic vacuum cleaner of sorts. We know that Jupiter gets approximately 2,000 to 8,000 times as many cometary impacts as Earth. So, perhaps one of the reasons extinction-level impacts are so uncommon here on Earth is that Jupiter had been a magnet for these kinds of comets and asteroids. This argument has even become part of the rare Earth hypothesis, which suggests that Earth is host to a unique set of conditions without which the evolution of complex life would be impossible. Not everyone agrees with this hypothesis though, and in any event, we're still a long way from proving it. So, while we might not know the exact likelihood of a massive comet or asteroid hitting the Earth, the impact of SL9 with Jupiter has certainly advanced our understanding of these events. Moreover, it was, without question, a spectacular moment that treated watchers to one of the most impressive action scenes ever witnessed by human eyes. Maybe one day we'll have the chance to see something bigger, but hopefully from not too close. While there have been other explosive events, like the 2022 Tonga volcanic eruption, for now, the winner is clear. The biggest explosion ever seen on a planet is Shoemaker-Levy 9, and by comparison, the competition looks like a drop in the bucket. So, science had seen firsthand the awesome impact potential of comets, but they still didn't understand enough about the nature and composition of comets themselves. The Halley Armada had collected some useful images and data, but to truly understand comets, it would take more than photographs. A more physical approach would be needed. Between 1999 and 2005, 2 probes were launched. Their mission was to interact with comets in ways that had never been attempted before. One would bring collection equipment that would allow it to scoop stardust right from the comet's icy tail to help scientists analyze the chemical makeup of these frosty harbingers. The second would take a more forceful approach. Rather than quietly collecting a smattering of space dust, the second probe would crash headfirst into the surface of the comet itself, exploding with the force of 5 tons of TNT, to see what could be learned from the resulting crater and debris. And yet, although these 2 missions were 2 different comets, through chance there was one comet that unexpectedly brought them both together, Tempel 1. Let's take a closer look at their story. In 1999, NASA scientists proposed a plan to hopefully answer some of the lingering questions about comets' internal compositions, structure, and origins. Of course, it would be difficult to understand the internal structure of comets by simply looking at their surface. To know what was going on, scientists would need to dig a little deeper. Their plan was to create a crater in a comet using an impactor spacecraft, which would collide with the comet at high speeds. As they would know the mass of the impactor and the speed it was traveling at, they could calculate from the size of the impact crater valuable information about the comet, whether its surface was a loose aggregate of dust and ice, or whether it had a hard, frozen shell, for instance. The comet they wanted to target was a short-period comet called Tempel 1, which had a nucleus of 8 kilometers long and 5 kilometers wide. Scientists weren't exactly certain what would happen when the impactor hit. Perhaps the impactor would punch straight through, like hitting a snowdrift, and not really create a crater at all. There were many theories, but scientists were eager to find out which was correct. NASA approved the project, giving it a budget of $330 million, and named it Deep Impact. You might have thought that this was a reference to the 1998 Hollywood film of the same name, but apparently the names for both the project and the film had been come up with independently around the same time. Quite the remarkable coincidence if so, as Deep Impact, the film, was about scientists trying to blow up a meteor that was on a collision course with the Earth by flying a spacecraft to it carrying nuclear warheads. There certainly seemed to be some similarities to the NASA mission, especially as NASA scientists worked on the film. I don't entirely buy NASA's claim of a coincidence. Although, fortunately for the Earth, there were some differences between the film and the mission too. Tempel 1's orbit was nowhere near the Earth's, and given the size of the impactor compared to the comet, there was no chance of knocking it off its current trajectory by more than a centimeter or so. It would be more like a fly hitting the front windscreen of a large vehicle. Additionally, nukes would not be necessary to create a crater on Tempel 1, or any kind of explosives for that matter. The sheer speed and kinetic force the impactor would have when it collided with the comet's surface would be enough to create the crater, which some predicted would be roughly 100 meters across and 30 meters deep. With the mission going ahead, scientists began work on the Deep Impact spacecraft. The spacecraft was actually made with two parts, the payload and another larger mothership to carry it and record the result of the impact. The second section was called the flyby. It weighed 601 kilograms, was 3 meters long, and housed scientific devices, solar panels, a debris shield, and two powerful cameras, the high-resolution imager and the medium-resolution imager. These would take photos of the comet after the impact, as well as help with navigation. The impactor itself was smaller, only 372 kilograms, but it was still smart and housed a camera of its own. This camera, the impactor targeting sensor, would take photos of Tempel 1 right up until the moment of impact, streaming back the images it collected to its parent, Flyby, which would then relay the images to Earth. There was considerable public interest in the mission, which NASA encouraged in 2003 by getting members of the public to submit their names to be recorded on a CD, which was placed on the impactor. Roughly 625,000 names were collected in this way, to be carried directly to Tempel 1's surface. On top of that, NASA timed the impact to take place on the 4th of July, American Independence Day. While this may have been because it was one day before Tempel 1's perihelion, and its proximity to the Sun may have produced clearer images, I suspect that the more likely reason for this date was that American scientists liked the idea of a large cosmic firework. Deep Impact launched on the 12th of January 2005 on a Delta II rocket. But then a problem hit. Within a day of leaving the Earth's orbit, Deep Impact's onboard computers switched itself to safe mode, which it would only do if there was a fault. Something on board was apparently overheating. This gave scientists a bit of a scare, but fortunately the cause of the problem was quickly found to be a minor programming issue. Acceptable heat tolerances had been set too low, so Deep Impact thought its thrusters were overheating, when in reality they were just fine. Engineers corrected the issue, and Deep Impact was able to properly begin its mission. The spacecraft spent the next 6 months traveling to its rendezvous point with Tempel 1. In that time, it traveled 429 million kilometers. It had to course correct twice on the journey, but this was actually impressive, as it had originally been planned for there to be 3 course corrections. One was just so precise that the other was deemed unnecessary. On the 25th of April 2005, Deep Impact caught its first glimpse of Comet Tempel 1. Of course, NASA scientists couldn't manually guide Deep Impact as there was a several-minute signal lag. Deep Impact and Tempel 1 were now roughly 130 million kilometers away from Earth, more than twice the closest distance between Earth and Mars. Deep Impact's smart onboard programming would have to guide it in for the final leg of the journey. On the 29th of June, the impactor successfully released from the flyby and positioned itself into the comet's flight path to crash into it head on. This was done for a few reasons. First, the front of the comet was in sunlight, which would allow for better pictures to be taken. Second, it would allow a greater accumulated speed to be reached, resulting in greater kinetic force. And on the 4th of July 2005, just 1 second out from the anticipated arrival time, the impactor hit. And what a magnificent spectacle it produced. Scientists were thrilled that they had struck so accurately. Deep Impact's payload had been traveling at 37,000 kilometers per hour and had struck with a force of 19 billion joules of kinetic energy. This produced the bright flash you see here, the energy of which is roughly equivalent to 5 tons of TNT. This flash was much brighter than scientists expected. It lit up the surface of Tempel 1. However, ironically, the success of the first part of the mission caused an unexpected negative side effect. A large dust cloud was kicked up by the impact, which obscured the flyby's view of the impact crater. Dust outgassed from the comet for the next 13 days, peaking 5 days in, which made it hard to see the results of this interstellar bullseye. Although it did offer some interesting insights into the internal pressures going on inside the comet. Around 5 million kilograms of water and between 10 and 25 million kilograms of dust were ejected from Tempel 1 in that time. Fortunately, scientists were able to rely on other eyes, at least to capture images of the explosion. The collision had been observed through numerous other telescopes on or around Earth, including Hubble, Swift, and even many amateur astronomer telescopes. Still, this was a serious problem. Although this outgassing was fascinating to record, the primary purpose of the Deep Impact mission was to take photographs of the crater caused by Deep Impact. Without images of the result, many of the questions about Tempel 1 would remain unanswered, like about its structure and composition. Like a partially unwrapped gift, Tempel 1 had been opened, but it had not yet been seen what lay inside. Some other craft would be needed to complete Deep Impact's unfinished mission. Fortunately, another craft capable of doing so had already been launched, and, having completed its own previous mission, was now drifting serenely through space. It was about to receive another task. It's time to talk about Stardust. Let's go back to the late 1990s, when cometary science was even more patchy. Although by this point we had sent 6 probes up to visit these enigmatic celestial bodies, not very much was known about their origins. It was believed at the time that comets were foreign visitors to our solar system, older than the Sun, having been formed from the loose pre-solar grains of dust that orbit other stars, before drifting through space towards us, only to be caught up in the Sun's gravitational pull. It was believed that this theory could be confirmed by traveling to one of these comets and picking up some of this loose dust, or stardust, that surrounds them in space. By examining the isotopic composition, scientists would be able to tell if it was unusual when compared to the dust given off by our own star. However, this was a challenging mission. As is often the case, it came down to a question of speed and energy. Comets travel through the inner solar system at speeds reaching 160,000 kilometers per hour. While it was possible for a probe to try and match that speed and come up alongside it, this had to be done without needing too much fuel, or the weight of the craft would be too heavy and thus too expensive to get into space in the first place. Initially, Stardust had nothing to do with Tempel 1. For this mission, scientists selected a comet known as Wild 2. They believed that they would be able to get Stardust alongside Wild 2 at a relatively low velocity. However, this velocity would still be around 6.5 kilometers per second, or 23,400 kilometers per hour. As you can imagine, catching even particles at that speed would be extremely challenging. Although particles would likely not do too much damage to Stardust, being too small to really impact it, it would do irreparable damage to the particles themselves. When an object crashes at 23,400 km per hour into a surface, the odds of it keeping its original shape and structure are incredibly small. Scientists would not learn much about the structure of these particles if they smashed those particles into pieces, not to mention the warping effect all that kinetic energy being suddenly converted into thermal would have on the molecular bonds involved. So, what was their solution? What was their mechanism for catching objects traveling at those speeds? Well, much like how an airbag softens the blow for you if you are involved in a car crash, scientists realized that they would need an airbag of their own, something that would not halt the particle all at once, but would reduce its speed over a longer distance, thus reducing the amount of crushing deceleration involved. For this, they found an incredible material that was basically air, solid air. They decided to use aerogel. Aerogel is a fascinating substance that was discovered in 1931 by Samuel Kistler when he made a bet with fellow scientist Charles Learned about jelly. As you've probably seen if you've ever made it yourself, jelly is formed of two parts. Firstly, a relatively solid structure that acts like a kind of sponge, and secondly, water. When you add water to solid cubes of dense jelly, it absorbs the water and expands into the wobbly substance we are familiar with. If you were to extract the water, the solid part of the jelly would normally contract again. Kistler's bet with Learned was to be the first one to remove all of the liquid from the jelly without making it shrink. In short, to make a jelly that was entirely filled with air, an air jelly. Without going into all the details, Kistler won his bet and at the same time invented the first aerogel. Aerogel is a fascinating substance as it is usually over 99% air and yet has the structural strength to support bricks. Nowadays it tends to be made from silica composites rather than jelly, but can be made from a wide range of materials. It is incredibly light and is, strangely enough, an even better insulator than regular air. And most importantly for Stardust, when particles hit it, it would offer just the right amount of resistance to slow down the particle without denaturing or destroying it. The trails left behind in the aerogel would also be useful for scientists to spot where a particle had been captured. Stardust was fitted with a tennis racket-sized aerogel collector tray made up of 90 blocks of aerogel 3 cm thick, with over 1,000 square centimeters of surface area, which would be deployed from inside the main body whenever sampling was to take place. Stardust would also capture from the interstellar medium to allow comparisons and to learn more about the dust in our own solar system. Once it had collected these samples, it would store them on a sample return capsule, which would be fired back towards the Earth for re-entry and collection. This SRC was 80 cm by 50 cm, weighed 45 kilograms, and came fitted with an aero shield, navigation recovery aids, and a parachute. Also on board Stardust was a navigation camera, a cometary and interstellar dust analyzer, and a dust flux monitoring system, among other scientific devices. The probe launched on the 7th of February 1999 and spent the next 5 years traveling through space, passing the asteroid 5535 Anne Frank along the way, which it took some photos of. But on the 2nd of January 2004, it finally arrived at its target, Comet Wild 2. And what it found was immediately extraordinary. Scientists had not expected much from Wild 2. Some NASA scientists described their expectation of it to be a rather bland object looking somewhat like a black potato. However, this is not what they found. Instead, the surface of Wild 2 was covered with spiky pinnacles hundreds of meters tall, cliffs, massive holes jetting dust and gas out into space, even on parts of the comet that were pointed away from the sun, and thus were expected to be less reactive. In short, the surface of the comet was unexpectedly alive and self-renewing. Something else was just as notable for its absence: craters. Unlike almost every other body in our solar system with surfaces exposed to space, there were no craters on the surface of Wild 2. This puts it in stark contrast to places like Mars or our own moon. Given the period of time Wild 2 is thought to have existed, it surely must have encountered other objects which impacted with it. So where had these craters gone? It shows that the comet's surface can either be self-renewing or active, reducing signs of visible craters over short time frames, astronomically speaking. And of course, during this flyby, Stardust had its aerogel collector exposed, and it was rapidly collecting dust samples. Just listen to the frequency in which dust struck the spacecraft. The samples were carefully stowed away, and upon reaching the vicinity of Earth, Stardust ejected the SRC. The angle of approach had to be just right as it was traveling at tremendous speed. If the approach angle was too low, it would just skim off the atmosphere and fly back into space. If the angle was too high, the heat would disintegrate the capsule. So it was with great relief that the DC-8 NASA airplane monitoring the sky saw it approaching at just the right second and just the right angle. The SRC landed in the Utah desert where it was recovered, everything having worked and deployed just as it was designed to. And taking the samples back to the lab, scientists learned another completely unexpected fact about Cometville 2. It was not a visitor to our solar system at all. Unlike what had previously been believed, Cometville 2 had not originated from another star, it had been born from our own. By comparing the isotopic composition of the particles Stardust collected with the samples from our own solar system, it was proven that Cometville 2 originated from the solar system. And contrary to what all the ice on its surface might lead you to believe, the rock at its center was formed under white-hot conditions. Chondrules and calcium-aluminium inclusions were both found among the samples Stardust collected. These are structures that only form under incredibly hot conditions and can be found in other asteroids between Mars and Jupiter. So scientists had to rethink their theory that comets formed in cold conditions at the edge of solar systems, even if they do spend some time there. Both fire and ice go into making comets. And thanks to the careful, delicate way that the particles had been collected, scientists were able to find out one last surprising thing: the amino acid glycine. Amino acids are the building blocks that make up proteins, that are vital for all living things. Although this does not mean that there was anything alive on Cometville 2, this does lend weight to the idea that it was from comets such as this, crashing into our Earth millions of years ago, that life's first building blocks found their way to our planet, which I'm sure you will agree offers a tantalizing glimpse into our own origins. Given all these discoveries, you might have been forgiven for thinking that Stardust's work was done. But NASA is always reluctant to waste perfectly good spacecraft if they have more to give, and Stardust still had fuel in the tank. And so, when the question arose in 2006 of how NASA could capture that close-up image of Tempel 1, Stardust's name was put forward. This would prove to be an interesting opportunity. Stardust was calculated to have enough fuel to make a 6-year journey around the solar system to arrive at Tempel 1. This would represent the first time a comet was visited and then revisited years later, providing an intriguing chance to see how Tempel 1 had evolved over the intervening years. Deep Impact only imaged about 1/3 of Tempel 1's surface as it flew past, but even that was enough to identify fascinating geological features: layered terrains, smooth flows that contrasted sharply with the rougher terrain around them, crater-like vents and cliff faces. It would be incredibly insightful to see how these had changed in the time Tempel 1 had orbited around the Sun. Stardust would be able to take images of things previously unseen, giving even greater coverage of the rich geological history of the comet. There were other advantages to using Stardust. It would be significantly cheaper to use equipment that had already been launched than to develop and launch something new. Stardust shielding was even designed specifically with cometary exploration in mind, which certainly came in use for reasons I'll go into later. It had all the camera equipment it needed to take precise images. And so, Stardust was approved and was given a new name to match its new assignment: the Stardust New Exploration of Tempel 1 Mission, or Stardust Next. Of course, achieving this goal wouldn't be easy. Course corrections had to be made years in advance to conserve fuel and make sure Stardust arrived when it was supposed to. This made things complicated, given that Tempel 1 didn't just remain static as it traveled. it spins once every 40 hours. So it wasn't just a case of figuring out how to get Stardust to meet up with Tempel 1. NASA had to make sure it happened when Tempel 1's impacted side was facing the Sun and facing Stardust once Stardust flew past. In effect, even though Tempel 1 was not easy to see clearly, they had to calculate all the spins that Tempel 1 would make a full year ahead to ensure the arrival time matched up. With Stardust's diminished fuel reserves, there would be little room for error. Incredible precision and excellent models would be required. As such, NASA enlisted the help of dozens of observatories around the globe. Tempel 1 was little more than a tiny dot in the night sky, thus it was impossible to track through its surface features, which were indistinguishable at that distance. However, its asymmetric shape meant that its brightness fluctuated as it traveled, dimming as a narrower profile was pointed our way, then brightening as the wider profile rotated into view, in regular intervals that allowed a detailed model to be created with a high degree of certainty. Scientists counted the spins as Stardust traveled. 1, 2, 3, knowing that if they missed a single count, it would potentially mean the failure of the primary mission objective. Their model needed to be perfect. Stardust traveled for years through space, engaging in one Earth gravity assist and multiple laps around the Sun before timing its final maneuver a full year before it would arrive at Tempel 1. The burn would alter its arrival time by a small yet significant 8 hours. Stardust was now locked in. A year later, as it closed in on the comet, Stardust shields began to detect sounds as tiny particles began clattering off it. Tempel 1 was still ejecting dust and small rocks into space. Stardust was hit dozens of times. Although these rocks were tiny, only a millimeter at most, some of these hits had enough force to go through the front of Stardust, cutting through a graphite cyanide honeycomb sheet as thick as your finger. Still, Stardust survived the barrage, and on the 14th of February 2011, Stardust made its flyby. It passed at a distance of 181 kilometers and took 122 images. I find it amusing that scientists waited for another holiday for a Tempel 1 visit. They'd chosen Independence Day for their initial impact. Here, on a less violent visit, they chose Valentine's Day. Scientists had to wait for hours for the images from Stardust to arrive back, but when they did, NASA saw that they'd managed another bullseye. They'd correctly predicted the rotation of Tempel 1 to an accuracy of a single degree. Right on Tempel 1's surface was the crater that had been left by Deep Impact's payload. The mission was a success. From the images Stardust took, scientists were able to calculate that it was approximately 150 meters across, so 50% larger than they were predicting. From this, they learned that the surface of Tempel 1 was a very fluffy material, similar to Halley's comet before it, but made from more dust than was expected, and finer in substance than a powdered snowbank. The surface was incredibly porous. In fact, they were able to estimate that 75% of the comet was actually empty space, the whole thing held loosely together by gravitational forces. From analysis of the plume that had been ejected from Tempel 1 after the impact, scientists were able to identify several interesting material components, including clays, silicates, sodium, and even organic material. Not only that, but they were able to see other changes that had taken place on Tempel 1's surface. 3 pits that had formerly existed had merged to become one. A cliff face had eroded back around 20 to 30 meters. This indicated that Tempel 1's surface was a dynamically changing place, like Vil 2 had been, leading to interesting questions about how these formations had formed in the first place that scientists could now puzzle over. So, Deep Impact's mission finally had closure and had been a resounding success. But this was not the end for Deep Impact. Following in Stardust's footsteps, Deep Impact's flyby was later given a new mission entitled Epoxy, or the Extrasolar Planet Observation and Deep Impact Extended Investigation. which in 2007 saw it heading off to investigate other comets and taking hundreds of thousands of photos before ultimately dropping out of contact in 2013. But by then, Deep Impact had already done significant amounts to advance our understanding of comets and our solar system. What about Stardust? After its extended mission, scientists saw that there was still a little fuel left in its tank, so it ran with it. Firing it for as long as it could, scientists checked to see if their models of how much fuel Stardust held matched up with the reality. To its last breath, Stardust kept doing science until the end. When at last all its fuel was used up, it sent one last transmission to Earth to acknowledge that it was being turned off for good. Now, it finally rests among the stars. It is not just through telescopes on Earth or through probes in space that we have watched comets in our sky. One view came from a machine looking up at a very different sky, on another planet entirely. The planet, Mars, and the machine, the Opportunity rover. In 2013, Opportunity was beginning its exploration of Endeavour Crater. As this was going on, a visitor from the outer edges of the solar system was hurtling towards Mars. Its trajectory would take it just 130,000 kilometers above the planet's surface before it continued on towards the Sun. This visitor was again not an alien, but Comet Siding Spring, a visitor from the Oort cloud. Remember, the Oort cloud is found well beyond Pluto and the Kuiper belt. Millions of icy rocks in orbits that take millions of years to complete. Because it had such a long time to accelerate towards the Sun from the furthest point in its orbit, the trip from Mars to the closest approach to the Sun only took 6 days. That's 56 kilometers per second. However, because of the close flyby of Mars, it meant that the spacecraft on and around Mars were actually in a better spot to witness Comet Siding Spring than we were on Earth. Mission controllers of the various missions were also a bit nervous about the dust particles that are ejected from the comet traveling at that speed, potentially impacting and damaging spacecraft in orbit around Mars. As such, Hubble, as well as spacecraft around Mars, all began observations of this visitor. Fortunately, mission controllers had already had some practice at this with Comet Ison, another comet that passed by Mars only the year previously. Comet Ison, however, was 80 times further away than Siding Spring would be, too far and too dim for Opportunity to spot. And unfortunately, it was day just as Siding Spring made its closest approach to Mars, but Opportunity was able to snap a couple of photos of it just before dawn. Can you spot it? Here's the annotated version of the same image. I mention this story as it led to an interesting observation. As the comet passed by, none of the spacecraft were damaged by ejected dust particles, but what they did observe from this flyby was completely unexpected. Comet Siding Spring plunged Mars's weak magnetic field into chaos, albeit temporarily. Unlike Earth, Mars doesn't have a magnetic field generated from within its core. Its magnetic field comes from plasma high up in its atmosphere, which generates a very weak charge. This is enough to deflect solar wind coming from the Sun, but solar storms from CMEs and solar flares push past this induced magnetic field, stripping away atoms from the atmosphere. Comet Siding Spring had a very similar effect on Mars. Comets are also surrounded by a magnetic field, again induced from interactions with solar wind, this time with the comet's atmosphere, or coma. A comet's coma can reach out for millions of kilometers from the comet, meaning that as Siding Spring passed Mars, Mars was enveloped in its coma for a good few hours. This merged both magnetic fields for the duration of the event, with charged particles from both objects interacting strongly with each other, and the atmosphere of Mars actually lost some particles to space as a result. Sometimes, surprising observations like this can come from machines that weren't originally intended to study comets at all. The Solar and Heliospheric Observatory, also known as SOHO, recently celebrated its 25th anniversary in space. During these 25 years, It has observed the solar wind, watched out for dangerous coronal mass ejections, and observed the atmosphere of the Sun. An unintended consequence of its observations around this region were the discovery of over 4,000 sun-grazing comets, most of which we had no idea existed until they came into SOHO's view. And SOHO isn't the only solar observatory. The Stereo spacecraft and the Solar Dynamics Observatory have all seen new comets. And what's so cool about that is that they weren't designed with that in mind at all. Sun grazers are comets that do just that. They graze the Sun as they pass, with the closest parts of their orbits taking them within a hair's breadth of the Sun's surface. Often they will pass through the Sun's huge atmosphere, called its corona. These comets are mainly long-period comets, comets whose orbits take hundreds to thousands of years to complete. Because of their orbit's extreme elliptical nature, they build up tremendous speeds as they approach the Sun, sometimes accelerating to 0.2% of the speed of light, an absolutely incredible speed for a particle, let alone a house-sized object. The majority of sun-grazer comets actually all originate from one large comet that was ripped apart several hundred years ago. This group of sun-grazers, shown in red in this video, is known as the Kreutz sun-grazers. What tends to happen over time is that the fragments from the larger comets spread out, meaning that there is probably a steady flow of them. As the largest of these comets also pass by the Sun, they too break apart into even smaller comets. And the reason we believe most sun grazers originate from the same comet? Well, they all tend to follow the same orbital path. The brightest comet in the last millennium, known as Comet Ikea-Secchi, was probably a fragment. It was so bright as it approached the Sun that it could even be seen during the day. You may have heard of another famous fragment of this comet that dimly illuminated the sky in the southern hemisphere in 2011, called Comet Lovejoy. While Comet Lovejoy wasn't as bright to the naked eye, it did make for some very impressive long exposure images and was seen by all the Sun observing satellites. Comet Lovejoy was not expected to survive this encounter, as it would have been in the Sun's 1 million degrees Celsius corona for more than 1 hour. However, astonishingly, it fizzed away from the other side of the disk, mainly intact, although probably severely impacted from the experience. The same thing happened to another comet, Comet Ison. You may remember that Comet Ison was expected to be a bright comet, potentially visible to the naked eye when it passed by the Sun in 2013. Alas, that wasn't to be. However, it still made for good viewing for the Sun-observing satellites. Ison's approach was bright and impressive, and upon reaching the other side of the Sun, it faded out. Scientists can't be sure if the nucleus survived or not, but if it did, there are certainly no volatile substances on it anymore. All that's left is probably dust. However, these are some of the biggest Kreutz sun grazers we've ever observed. Their nucleuses maybe being a few hundred meters in diameter. Some of the smaller comets were not known about until they actually came into the view of a Sun-observing satellite. Due to their small size, being only tens of meters across, many of the smaller comets were completely snuffed out by the Sun immediately after passing by too closely, which means unfortunately they were vaporized pretty much immediately after they got discovered. Sometimes they will pass around the back of the disk of the Sun, never to re-emerge from the other side. Although at other times, the angle of the comet's orbit means we can witness this vaporization as it happens. At this distance from the Sun, the heat is incredible and the gravity is overwhelming. The icy comets not only evaporate quickly, but the rocky elements of them are also ripped apart from tidal forces. Our own close encounters with comets show that they tend to be structurally weak and very porous, sometimes nothing more than a pile of rubble held together by its own gravity. So combine that with the influence of the Sun, and even the largest sun-grazer comets will come away heavily scarred. Now, there's an interesting phenomenon that happens when a sun-grazer passes by the Sun, and that is that a CME will go off at the exact moment the comet passes by. There are numerous examples of this. However, scientists are still of the opinion that there is no mechanism for a sun-grazer to cause a CME. These comets simply aren't big enough to have any consequential impact on the Sun, so it is currently believed that these examples you see here are purely coincidental. What scientists enjoy about sungrazers, though, is that while we can't send probes deep into the sun's corona, it's simply too hot for that, and even the Parker Solar Probe doesn't dive in too deeply, or else it would risk annihilation. We do have these thousands of comets that are willing to take the plunge for us. And comets are perfect for us to observe what we are looking for, which is to better understand the magnetic fields within the corona, so that we can better predict CMEs and space weather generally. Look how as a comet passes by, its tail wiggles. The particles in the tail get heated so much they turn to plasma, which can easily be seen by the UV cameras of the satellites. Plasma reacts strongly to magnetic fields, so the wiggle you see in the tail is believed to be due to the way in which the tail interacts with the magnetic field lines in the corona. Currently, space weather is something we don't have a complete understanding of, so as more comets pass through, the more we will begin to understand that environment. But when it comes to expanding cometary science, nothing can beat a dedicated mission. After the Halley Armada, Stardust and Deep Impact, we'd taken numerous images of comets. We'd caught the dust that made up their tails, and had even crashed into one. But that left one logical step to try next, to attempt to land on a comet's surface. And that's what ESA tried to do in 2015. The Rosetta-Philae spacecraft that visited 67P Churyumov-Gerasimenko was perhaps ESA's most ambitious mission. NASA isn't the only one that has performed breathtaking missions to other worlds, and personally, the Rosetta mission is ESA's answer that really holds its own against some of the impressive stuff NASA has done. However, not everything went according to plan with this mission. Philae, the lander part of the mission, was expected to perform scientific experiments on the surface of the comet for 5 months, but it didn't manage anywhere near that. For our last stop on this tour of the evolving world of cometary science, let's explore the highs and lows of Rosetta-Philae's mission to 67P. Rest assured, we've saved the best and strangest comet for last. 67P is currently a Jupiter family comet, although it was once a Kuiper Belt object. The Rosetta-Philae mission launched on the 2nd of March 2004 on board ESA's own Ariane 5 rocket. It was initially set to be launched on the 12th of January 2003 and had a totally different target. But the Ariane 5 rocket program had a major failure a few months previously with another mission, meaning all launches were grounded until they could determine and fix the problem. With the launch window for that comet missed, a new target had to be chosen, and ESA settled on 67P due to the ideal position in its orbit. Once in space, the Rosetta spacecraft had an eventful 7-year journey on its way to the comet. As is often the case with missions to the outer solar system, it needed some gravity assist to get that far out. It had a flyby of Earth in 2005, and then a flyby of Mars in 2007. This Mars flyby was pretty risky. It would skim the planet just 250 kilometers above Mars's surface. Also, during this flyby, which lasted 15 minutes, it would be completely in Mars's shadow, and because the craft is solar powered, the craft had to go into standby mode. Rosetta's components had to be kept warm by onboard electric heaters to avoid damage from the harsh environment of space. However, its batteries were never designed to run by themselves for long. Its power levels got dangerously low, and had they completely drained, then it would never have been able to switch itself back on after the flyby. Nothing could be transmitted back to Earth as this was happening, so mission controllers simply had to wait and hope the spacecraft would turn itself back on. They called this the €1 billion gamble. But the flyby was a success, and the mission continued on, even managing to capture some photos of Mars in the process. The spacecraft flew by Earth a second time in 2007 at a distance of 5,700 kilometers. Interestingly, during this flyby, it was spotted by ground-based telescopes and was presumed to be a near-Earth asteroid, and so was added to the Catalina Sky Survey as a 20-meter potential Earth impactor asteroid. It wasn't until a few days later that the mistake was found. Heading back into the solar system with increased speed from the flyby, its trajectory took it past 2867 Steins, a small 5-kilometer asteroid in the asteroid belt beyond the orbit of Mars, and these are some of the pictures it took. Rosetta did one final flyby of Earth in 2009, which finally gave it the boost it needed to reach the comet. During this last leg of the journey in 2010, it flew by another asteroid called 21 Lutetia, which is 100 kilometers in diameter. I think seeing both of these asteroids gives an interesting comparison between asteroids and comets, because as you are about to see, they look remarkably different. After visiting Lutetia, the spacecraft went into hibernation mode until 2014, when it started to approach the 4.5 kilometer wide comet Churyumov-Gerasimenko for the first time. After a number of burns with onboard thrusters, they aligned the trajectory of Rosetta with the trajectory of the comet. As Rosetta approached, these fantastic images started to come in, and they surprised everyone. The comet seemed to actually be a contact binary, full of jagged edges and sharp sides, cliffs, valleys, and crevices. It's a breathtaking sight to behold, and is really a lot more interesting looking than anyone had previously thought. But upon seeing these images, mission planners collectively thought, how are we going to land on this? The Rosetta-Philae mission has two parts: the orbiter, Rosetta, or the mothership of this mission, and a much smaller lander probe, Philae. Mission planners wanted Philae to land on the surface in order to closely examine materials making up the comet with a variety of different scientific instruments. They couldn't afford to have it fall over on its back upon landing, thus not providing any scientific data about this special object. So the first thing Rosetta did upon entering orbit was to map the unusual surface of the comet to find the ideal landing site. Apart from the non-spherical nature of the comet, another thing to consider was the amount of outgassing at any particular site. Remember, some parts of comets are very active, with lots of water being ejected into space, especially as the comet approaches the Sun. Landing on an outgassing site was seen as too dangerous for the health of the Philae lander, so a less active site was chosen. So, on the 12th of November 2014, Philae was ejected from the Rosetta mothership and started its extremely slow descent towards this section of the comet. Philae was equipped with 2 harpoons, which were due to shoot into the surface to stop the probe from bouncing on impact, as the escape velocity of the comet is only 1 meter per second. To give you some perspective, if you were standing on its surface, you could probably jump off it altogether. Its gravity would be too weak to pull you back. There was eager anticipation and nervousness at mission control as Philae descended, as due to all the many different factors, like the shape of the object, the outgassing, and the stray bits of comet debris in orbit around the comet, there was a lot that could go wrong. Philae eventually touched down on the surface, and as the spacecraft landed, it sent back a landing signal to mission control to say, "Job well done." What mission control didn't realize at that moment, though, was that their worst case scenario had just happened. The onboard harpoons hadn't fired, and although the probe had landed, it immediately bounced off the comet's surface. Commands were sent to it to start performing scientific experiments, but Philae was actually floating in space at that moment. There was a serious amount of confusion for a while, until they realized it hadn't properly come to a rest and was still in the process of bouncing. Luckily, the bounce's velocity was only 38 centimeters per second, meaning that it only rose 1 kilometer from the surface before eventually coming back down again. Over the course of 2 hours, it bounced 3 times before eventually coming to a rest. Sadly though, it was well away from its initial landing site, and came to rest here in a region that was often obscured from the sun, meaning it would quickly run out of power due to its solar panels not getting much light. On the other hand, mission controllers felt extremely fortunate that it had appeared to land the right way up, so that it could still collect at least some valuable scientific data. Mission controllers suddenly had a rush on their hands to collect as much scientific data as possible before the batteries ran out. Their estimated 5-month mission was suddenly cut down to less than 60 hours. By the 14th of November, battery power had run out and communication was lost. Amazingly, in June 2015, with increased exposure to the Sun due to the comet's closer approach during its orbit, the little Philae lander was able to turn on again and sent a signal back to Rosetta. Although the signal was intermittent, the lander was able to perform one last science experiment, which was the Concert radar experiment, and it sent back its results. As time went on though, the comet became more active as it got closer to the Sun. It originally only outgassed 500 grams of water and dust per second, but at this point it was outgassing 300 kilograms per second, which meant that in order to keep Rosetta safe, it had to orbit further and further out. By the 9th of July, Philae transmitted its last signal and then went quiet forever. It wasn't until September that mission controllers eventually found the final resting place for Philae. You can see its legs sticking out just by here. Knowing where Philae landed was important, as it would put the scientific data it collected into perspective. So, what did Philae discover while on the surface? Did it put those 60 hours to good use? And what about Rosetta from orbit? Was it able to make some groundbreaking discoveries? Arriving at this comet was a revelation to mission planners by itself. So far, nothing in the solar system that had been examined closely looks anything like 67P, which just goes to show that not all comets are identical. It's about 5 kilometers across at its longest point, and has 2 lobes which are joined by a narrow stretch of material in the middle. This by itself was somewhat unusual, but it is also very jagged, unlike a lot of asteroids that we visited. Once again, during the course of the mission, it was discovered that the surface of this comet is quite changeable. If we look closely at the neck connecting the 2 lobes, it becomes apparent that this section is under mechanical stress. If we look at these rocks, we can see that there are fracture lines running through them. Fracture lines are also apparent from a different angle. Scientists have used models based on fracture lines found all around the neck region to determine that these fractures permeate deeply inside the comet, up to 500 meters below the surface. It seems that as the comet rotates about its axis, the 2 lobes are pulling away from each other, thinning the neck region gradually over time. Huge 10-meter boulders were observed being displaced by this mechanical stress, as well as from the volatility on the surface, sometimes by up to 100 meters due to the comet's weak gravity. This also implies that the comet is really quite brittle and porous, which scientists found very interesting. As well as fracture lines, layers can also be seen, implying that during its formation, this comet was built up gradually over time. However, even though it is brittle, the surface of the comet is a lot harder than expected. Scientists thought the initial landing site for Philae would almost be soft and fluffy, kind of like the dirty snowballs seen in previous missions, but this was not the case. As Philae came to land on 67P to directly interact with the comet, it found that its final resting location was solid, thought to be water ice, with a thin layer of dust. Mission controllers for Philae tried to get a sample of the soil, but as you can see, it was eventually found out that Philae ended up at an awkward angle, and so wasn't able to get its drill into the surface. However, readings were still able to be obtained by examining the material on the craft itself, which had ended up on Philae after the bounces. Of the surface material examined, it was determined that there were 16 different organic compounds, 4 of which had never been detected on a comet before. While organic compounds do not mean life, life is based on organic compounds. While Philae wasn't able to get too many readings of the surface, Rosetta was also able to get some samples of the comet by collecting some of the dust snow that was ejected away from the comet itself into space. One of the most impressive shots Rosetta was able to take is this video of dust particles and cosmic rays shooting off in all directions, with the stars moving in the background. All the particles are visible because Rosetta is looking at the night side of the comet, meaning increased exposure of the camera can pick up these interesting visual elements. Throughout the mission, Rosetta collected roughly 31,000 dust particles, and interestingly, their composition didn't change throughout the course of the mission, even as the comet became more active, meaning that the whole nucleus of the comet is likely to be consistent throughout. The dust particles consisted of complex, organic, carbonaceous material mixed in with sodium, magnesium, aluminium, silicon, calcium, and iron. What separates this material from an asteroid's, however, is the presence of an abundance of hydrogen and oxygen. It is theorized that asteroids have been heated a lot longer than comets due to their closer proximity to the Sun, which has stripped the hydrogen from their compositions. Comets, however, have been kept away from the inner solar system for much of their lives, meaning these dust samples are pristine relics from the formation of the solar system, and potentially even the molecular cloud the Sun would have originated from. Oxygen was an unexpected find, as it's highly reactive, and if there is hydrogen around, it will usually bind together to form H2O. Carbon and hydrogen were also detected in the comet's tenuous atmosphere by Philae. The dust particles you see here are tiny. The biggest that was collected was only 2 millimeters across. But interestingly, it is particles just like these ones that light up the sky during a meteor shower here on Earth. What these views do give us, though, is an insight into the material that formed the solar system, so we can see where our solar system evolved from. By now, we understand that comets tend to be very dark, only reflecting 3 to 4% of the sunlight that falls on them, which you maybe wouldn't expect from something that is considered to be icy. But actually, not a lot of the ice in a comet is exposed to the surface directly. Most of the comet is coated in this layer of complex carbonaceous dust, which is darker than asphalt. These colored sections in this time-lapse show the exposed water ice. As you can see, it's not a very big percentage of the comet itself. Light that isn't reflected is instead absorbed, heating the volatile material beneath the dust layer, causing outgassing of water and carbon dioxide, which also blasts the tiny dust particles Rosetta picked up into space. As these are ejected at escape velocity, they fall behind the comet and form its tail. Zooming out a little bit and looking at comets generally, let's talk about why comets have 2 tails. One tail follows the orbit of the comet. This tail is the dust tail. The dust tail is illuminated as sunlight reflects off it. The other tail consists of the volatile material, the water and carbon dioxide that outgassed from the comet. This tail follows the direction of the solar wind, and these particles are illuminated through ionization and interactions with the charged particles from the Sun. It is often hard to see comets with your naked eye on Earth, but every so often a comet will outgas enough material that it is visible. In the northern hemisphere, the last bright one I saw was Hale-Bopp in 1997 when I was just a kid. But I did also recently see Comet Neowise in 2020. What an amazing sight it was. You guys in the southern hemisphere have been a bit luckier with comets. You've had Comet McNaught in 2007 and Comet Lovejoy in 2011. Going back to 67P, there was one other very big reason why the Rosetta-Philae mission happened in the first place. And that was to see if water on comets is the source of water on Earth. Before this mission, the theory was that Earth was bombarded by comets early in its development, back when the solar system was a lot more chaotic. Considering a large portion of comets are water ice, these could have given the surface of Earth the water we enjoy today. But as it turns out from Philae's findings, this was not the case. Scientists were able to determine this from the water vapor's deuterium ratio to hydrogen, which is significantly different from Earth's, just like it had been on Halley. Here's Earth's ratio, and here's 67P's. As you can see, they are very different. Only 2 comets have had their water vapor measured for deuterium directly, 67P and Halley's comet, and neither suggests that comets were the source of water on Earth. Instead, this data gives more weight to models that suggest asteroids are the source of water on Earth, even though their water content is generally very low. But perhaps there was more water on them billions of years ago. Maybe we simply don't see that much water now because all the volatile substances on asteroids have already burned off. In any case, it seems that Earth would have had a rough time during its formation. Rosetta and Philae were also equipped to detect if the comet had a magnetic field, like the one on Comet Siding Spring that had plunged Mars' own magnetic field into chaos. Initially, scientists thought they discovered the presence of a magnetic field on the comet, the hum of which they converted to audio sound. This is what it sounds like. However, it turns out this was not the result of a magnetic field, as curiously, Philae could not detect the presence of a magnetic field on the surface, but rather this sound is the solar wind's interaction with the comet's atmosphere. In fact, because of this interaction, the atmosphere and comet nucleus are completely devoid of any magnetic field, which is called a diamagnetic cavity. Rosetta finished its mission by crashing into the surface of the comet. As the comet was going further away from the sun, there was no guarantee it would have enough power for its heaters. So in order to maximize the science gained, mission controllers commanded it to perform a controlled descent into the comet. During this descent, it took multiple images, which you can see in this time-lapse, providing better resolutions of the comet than ever before, until it finally hit the surface and all communication was lost. Between Rosetta and Philae, they have opened our eyes to what the solar system was like during its formation, and have provided data that has and will yet lead to many discoveries. Here's hoping for many more missions like this one in the future. Comets are truly fascinating things, and it was thanks to the incredible work of the Stardust probe and the Deep Impact mission that we were able to learn a great deal about their inner composition and workings. While still retaining their beauty, we have pierced through their layers of enigma. We understand that they are not some foreign visitors, but originate here, from our own solar system, and may have even led to the blossoming of life itself on this planet. And it was human ingenuity and precision that allowed these discoveries to be made. So, the next time you see a comet, with its beautiful tail flaring out across space away from it, it will no longer be quite so mysterious or foreboding. They may even be the reason you are here today. But the thing I love most is that even now, there is still so much about comets to uncover. There will no doubt be many more missions to image and sample comets in the future. While once we looked up at comets in the sky and maybe made a wish, it turns out that visiting and learning more about them is no longer wishful thinking. Thanks for watching, and thanks to our crew of astronauts over at Patreon who help us make science knowledge freely available to everyone. Chasing the algorithm can be hit and miss sometimes, so your contributions help us keep making the content we love. And if you haven't already, but you want to join the Patreon, there's never been a better time to get in on the party. Just sign up with the link in the description. When you join, you'll be able to watch the whole video ad-free, see your name in the credits, and submit questions to our team. Once again, a huge thank you from myself and the whole Astrum team. Meanwhile, click the link to this playlist for more Astrum content. I'll see you next time.